You ever stop and think about what's really happening when you hit send on an email or load up a website? I mean, it feels totally instant, right? But underneath that one little click is this incredibly complex, super high-speed journey. Today, we're going to pull back that curtain and look at the fundamental rules that make the entire internet tick. So let's follow one single piece of data on its wild ride through this digital post office. And that's the big question, right? How can billions of totally different devices, we're talking iPhones, Androids, laptops, heck, even your smart fridge, all made by different companies, how do they all speak to each other so flawlessly? You'd think it would be total chaos, but the answer is actually, well, it's surprisingly elegant. Well, for any of that to work, everyone has to agree on a shared set of rules. You need a common framework that takes all this powerful technology and makes it smart. In the world of computer networking, it's not just one language. It's a whole stack of them, all working together in what I like to call the digital post office. Now, to get our heads around this, network engineers use this conceptual framework called the OSI Model. And don't worry, this isn't some strict protocol you have to memorize. Think of it more like a reference guide, or maybe the ultimate project management tool for the internet. It takes the massive task of, say, sending a cat video across the globe, and it breaks it down into 7 smaller, much more manageable jobs. So we're going to follow a piece of data on its journey, starting from your application, like your web browser, all the way down to the physical wires. And this whole process has a name. It's called encapsulation. The best way to think about it is like putting a letter in an envelope, then putting that envelope into a box, and then slapping a shipping label on that box. With each step, another layer of wrapping and instructions gets added, just like a package in the real world. All right, let's actually follow a single piece of data as it completely transforms from just a simple click in your browser into a physical signal. We're talking a literal pulse of light that can cross an ocean in the blink of an ad. We can kind of break this whole trip down into 4 big stages. We're going to start in the world of software, then we'll get the data ready for transport, then we'll give it an address, and finally, we turn it into an actual physical signal. So let's start at the top, in the world of pure software, and see how this journey gets started. So everything kicks off inside the software you're actually using. Those top 3 layers, application, presentation, and session, they all work together. The application layer, that's what you see and interact with, like your web browser. The presentation layer is kind of a translator, making sure the data is in a format the other computer can actually read, handling stuff like encryption. And the session layer? It just manages the conversation, keeping the connection open. All of that work produces the first block of digital info, which we just call data. Now, trying to send that huge block of data all at once would be super inefficient and honestly pretty risky. So the next layer down, the transport layer, it acts like a digital butcher. It chops up the data into smaller, more manageable pieces we call segments. And this part is so important, it stamps each segment with something called a port address. This is like putting a specific person's name on the letter. It tells the computer on the other end exactly which application this data is for. Is it for Chrome? Is it for Spotify? Or is it for your email? And this is where things get really clever. The transport layer has to decide how it's going to send those segments, and it's got 2 main choices. First, you've got TCP. Think of TCP as a luxury Cadillac. It's all about reliability. It's going to check and double-check to make sure every single piece arrives perfectly, even if it's a little bit slower. Then you have UDP. UDP is the sports car. It rips out all the safety features just to go as fast as it possibly can, perfect for things like streaming video, where who cares if you lose a pixel here or there. All right, so our segments now move down to the network layer. Here, they get wrapped in yet another layer of info, and they become packets. And this layer adds the most famous address of them all, the IP address. So if the port address was the name of the person on the envelope, the IP address is the full street address. It's that global identifier that tells the internet's routers exactly which device, anywhere in the world, this packet needs to get to. We are so close, we're in the home stretch now. At the data link layer, each one of those packets is placed into a final wrapper called a frame. This frame gets a local physical address, a MAC address, that's burned into your device's network card. Think of it like the specific apartment number inside the bigger building that is your IP address. And finally, the physical layer takes this fully wrapped and addressed frame and does something that is basically magic. It converts all those abstract zeros and ones into a real-world signal, an electrical pulse, a beam of light, or a radio wave. And this quote, I mean, it just hits the nail on the head, doesn't it? Seriously, think about it. What does Google Chrome feel like? You can't touch it, you can't smell it. It's totally abstract. The entire job of these bottom layers is to translate that virtual, abstract world of software into the physical world of things you can actually touch, like a copper wire or a Wi-Fi antenna. So that's the OSI model. That's the perfect 7-layer blueprint in theory. But when it came time to actually build the internet, engineers took a much more practical, get-it-done kind of approach. And that's where the TCP/IP model comes in. It's the battle-tested, real-world version that actually runs everything. And to understand why, you gotta go back to the late 1960s. The internet's ancestor, ARPANET, was a military project born out of the Cold War. The number one goal wasn't fancy features, it was pure reliability. They needed a decentralized network that could literally survive a major attack and still get the message through. And that relentless focus on reliability, on getting the message through no matter what, is baked into the DNA of the TCP/IP model. So as you can see here, the TCP/IP model doesn't try to reinvent the wheel. It just simplifies it. It takes those top 3 software layers we talked about, application, presentation, and session, and just bundles them all into one application layer. And it does the exact same thing at the bottom with the hardware layers. It's the same jobs, just being done by a more streamlined 4-person crew instead of a 7-person one. Okay, so we've been deep in the weeds with layers and models and all this abstract stuff, but why does any of it actually matter? Why do we even need these blueprints? Well, it all comes down to making our technology not just powerful, but making it smart. Let me give you a quick analogy. Think about a brand new, super powerful graphics card you buy for your computer. That amazing piece of hardware is completely useless until you install its software driver, right? The driver is the translator that lets your operating system actually talk to and control the hardware. And if that translator, that little software driver, is poorly written, well, it doesn't matter how powerful the hardware is. It's just like having a star athlete who's all muscle and no brains. They're completely lost without the playbook. All that incredible potential is just wasted. And that's exactly what these networking models are. They are the game plan. They're the brilliant, carefully designed set of rules that allow all of our incredibly powerful networking hardware to work together intelligently, making sure your email actually gets where it's going instead of just, running into a wall. These models were designed decades ago for a world of text and really simple data. And that leaves us with this huge, fascinating question. Are the blueprints that were designed for a dial-up world still the right ones for an age of virtual reality and AI? Or are we on the verge of needing a brand new game plan for the internet of tomorrow?